All right, let's go ahead and take a look at example one. In this example one, we're going to go ahead and use two different methods. The first method we're going to use is a method that really justifies a shortcut, which is the second method. So we'll start with the longer method. I'm going to go ahead and call this, go ahead and call this the rigorous method. And again, this is not the method that we're going to use really ever again, but it's what allows us to do the second method. So think of it as this is showing us all the nitty-gritty details, and then in the future we just kind of know that these details are happening in the background, and we don't have to explicitly state everything that's going on. So when we go ahead and take a limit as x goes to infinity of this expression here, it's a rational expression. That means we got a polynomial divided by another polynomial. And the way that we're going to actually compute this limit is by using this fact up here in remark number 1, and that is the limit as x goes to infinity of 1 divided by x is equal to 0. And if you've ever seen the graph of 1 over x, that checks out. As we go very far to the right, this approaches the x-axis, and it approaches 0. 1 over x is actually never equal to 0, but the larger x gets, the closer that gets to 0. So we're going to use this fact. And the way we're going to do this is we are going to try to make a bunch of 1 over x to the maybe first, maybe 1 over x to the 2, maybe 1 over x cubed. We really just want 1 over x raised to some power to show up, because we have the one limit law that says that if we have a limit of some function raised to a power, we can go ahead and just raise the answer to that limit to that same power and get the same answer. So that's what we're going to want to do here. So to do this, we're going to go ahead and notice that the largest term in both the top and the bottom, what is the largest term? The largest term is 3x cubed. Okay, so what we're going to do here is we are going to divide, or I guess you could think of it as multiplying, by 1 over x cubed. But we're going to do that to the top and to the bottom. So we get this kind of strange expression. And then this is a quantity that we can factor in, or sorry, excuse me, distribute in. Similarly, down here we can distribute this in which case, if we simplify everything, we have x squared divided by x cubed. That's going to just simplify to 1 over x. And we have minus 1 over x cubed. Down here in the denominator, we're going to have 3x cubed divided by x cubed, so that's just going to be 3. And then plus 4 over x cubed. And now we know from limit laws that the limit of a quotient is equal to the quotient of the limit, so we can basically move the limit upstairs and downstairs. And we can do that provided that the limit of the entire denominator is not 0. Now, based on this remark up here, that the limit of 1 over x as x goes to infinity is equal to 0, and using the limit law that the limit as x goes to, let's say, anything really, but let's say infinity of 1 over x to the n for any power n greater than 0 equals 0. We're really just taking this fact and using a limit law fact and combining them. So what's going to happen here is that this term will go to 0, this term will go to 0, this term will go to 0. So then ultimately what we have is the limit as x goes to infinity of 0 over 3, which is just 0. So that is the rigorous method. The idea here is that you divide top and bottom by the largest degree term. In my work that I just did, I didn't divide by the entire largest degree term because I didn't divide by 3, but whether or not you grab that extra constant, the leading coefficient, that doesn't actually matter. Like here we would have had this 3 cancel. That's really it. So this is just easier to write. All right, next thing, step 2, or method 2, is the method of dominating terms. And all we do in this method is really all about which term in the fraction, the expression that we're taking the limit of, which term is dominant, which one is the fastest growing. Okay, so what we want to do for these dominating terms, especially when we have something like a fraction, we want to look at what the top is doing and look at what the bottom is doing, sort of independent of one another. So let's first go ahead and identify that so first step here is we're going to pick off or identify the largest degree terms in top and bottom of the fraction. So the biggest term, the most influential term when x goes to infinity in the top is x squared. And in the bottom, that term is 3x cubed. So now if you remember what we did in the rigorous method, we found the largest degree term and we divided everything by it. Okay? So in this case, this 3x cubed shows up again. If we divide everything by that, we're going to do the rigorous method, and with a lot of algebra we can get to the final answer that this is 0. Instead, for this quicker method, we identify the dominating terms. So these are called the dominating terms. And then this method says that the original limit that we started with, so x squared minus 1 all over three x cubed plus 4. The method of dominating terms allows us to say that this limit is equal to the limit of the dominating terms. So we can just say x squared over 3x cubed. Then we can simplify the limit as if we had started with a brand new limit. And when we do that, we have 1 over 3x. And sure, we could pull out the 1/3 if we really wanted to. And then we see we just have the limit of 1 over x as x goes to infinity. No matter how you chalk it up, this is going to go to 0. So we get the same thing just by looking at the top, the biggest term in the top, and the biggest term in the bottom. Okay. And there's a little pattern here. Oops, technical difficulty there. What we'll find out in the next page is that there's actually a nice little method here that uses this fact. All we will do to evaluate the following 3 limits is compare the degrees. That's it.